Welcome to the start of probability. Today in exercise 11.2, we are going to review everything we've learned about probability, hopefully up to this point in year 10. So basic introduction, probability just measures the likelihood of an event happening from a scale of 0 being impossible and 1 being certain. Now, whenever we see these absolute numbers like 0 and 1, convert it to percentage by multiplying the decimal places by 100, and you'll get 0% for impossible. 1 will become 100%. So there are some key words you need to know. Experimental probability. This is an event's likelihood of happening based on your trials and experiments. A trial is basically an experiment, for example, flipping a coin, and we can figure out the probability experimentally depending on the number of trials you did and the number of successful trials that occurred. The next keyword, relative frequency. This is known as experimental probability. Different textbooks will use different sort of terminology. They essentially mean the same. Lastly, here we have event space or sample space. This is basically the total outcomes that can occur during our trial. So if we're flipping a coin, heads or tails, that is our sample space, and we can write it with the squiggly brackets H, T, H for heads, T for tails. So example 1, here what we have is an example related to sample space, experimental probability, and theoretical probability. Here we've got ourselves a spinner, and there's 4 quadrants, 1, 2, 3, and 4, just like a Cartesian plane. The spinner shown here is made up of 4 equal size segments. It is known that the probability that the spinner will land on any 4 of the segments in one spin is 1 on 4. To test if the spinner shown here is fair, a student spun the spinner 20 times and each time recorded the segment in which the spinner stopped. The spinner landed as follows in the table below. So theoretically, it should be a 1 in 4 chance every spin, but the student here who spun it 20 times got segment 1 5 times, segment 2 4 times, segment 3 8 times, and segment 4 3 times. So here it says for in A to list the sample space. So sample space, what we can do is now that's so just trying to think what other ways we can do sample space. So you might have seen it this way, or you might have seen it as omega, or you might have seen it as just an S. So maybe we'll just use an S to avoid confusion. All right, it doesn't really matter which one you use. Okay, they all mean the same. So event space here, sample space, means the same thing. We have section I, section double I, section triple I, and section 4, which is represented by IV. So event space, this equals sample space. So for those of you who grew up using Cambridge, sample space is, I think, what they used terminology-wise, but it means the same. Given the experimental result, determine the relative frequency for each segment. So this is the experimental probability. So let's say relative frequency for 1, we know it was out of 20. And for segment 1, we got an answer of 5, which we know is 1 on 4, because if we divided top and bottom both by 5, we would get 1 on 4. And this can also be written as 0.25 or 25%. Okay, I'm sure all this will be familiar to you. Next one, relative frequency or experimental probability. For segment 2, we've got 4 on 20, which is 1 on 5 if we were to divide top and bottom both by 4. This would be, damn it. This would be 0.2, which is 20%. Relative frequency. Triple I, we've got 8 out of 20, which is, what's that? 4 on 10, 2 on 5. So 0.4. How do we get these decimals? Just put 2 divided by 5 or 8 divided by 20 in your calculator. How do we get the percentage from a decimal? We multiply the decimal by 100. So 0.4 times 100 gets us 40%. And then relative frequency. Of segment number 4 is 3 on 20. 3 on 20 is just 3 on 20. There's no way of simplifying down. This is 0.15 and 15%. Okay, so that's the experimental results or experimental probability. In this textbook, they call it relative frequency, which means the same thing as experimental probability. Compare the results from the experiment with the known probabilities and suggest how the experiment could be changed to ensure the results give a better estimate of the true probability. So true probability, this is the same as theoretical probability. Okay, so theoretical probability of each segment is 1 in 4. As you know, with experiments, the less you do, the less the probability is to the theoretical. Okay, so because the student here spun the spinner 20 times, okay, there's a pretty good chance there's going to be a skew in the tally of the segments that the spinner landed on. So the more you do the test, the closer your experimental probability becomes closer to your theoretical probability. So here, to make sure the experimental probability is closer to the true probability or the theoretical, we need to spin the spinner more times. Okay, so spinning the spinner more and creating more trials will lead to the experimental probability to be closer to the theoretical probability. Right, let's move on. So the next part that you hopefully remember from previous years are two-way tables. And this is an easy way of displaying the sample space. So for example, if we were to roll a dice and a coin, well, the sample space could be, you might get a 1 on the dice and then a heads on the coin, and that would be represented as H1. You might get a 2 on the dice roll and then a tails, and that would be represented as T2. Now, if we take a look at example 2 here, 2 dice are rolled and the values on the on the 2 uppermost faces are multiplied together. Draw a diagram to illustrate the sample space. Okay, so keyword here, it's been multiplied together. All right, so here this would be 1 times 1. Oh, it's all underlined. It's all right, so this one here would be 1 times 1, which equals 1. 2 times 1, which equals 2. 3 times 1, which equals 3. Then we got 4, 5, and 6. This one here we have 1 times 2, which equals 2. 2 times 2, 4. 3 times 2, 6. 4 times 2 is 8, 10, 12. All right, and then you just multiply everything together and you get all the possible samples or possibilities that can happen when we roll 2 dices together. So here we've got 3, 4, 5, 6. 6, 8, 10, 12, 9, 12, 15, 18, 12, 16, 20, 24, 15, 20, 25, 30, and 18, 24, 30, and 36. So yeah, hopefully this makes sense. 6 times 6, 36. Classic multiplying tables. Theoretical probability. So long story short here, theoretical is in the perfect world. If we were to do these trials, it'll come out with the perfect probability. For example, if we were to flip a coin, we know in theory, we should have a 50-50 chance of landing it on heads or tails, which means the theoretical probability of it landing on heads is 0.5. Now, with experimental probability, we might do it 80 times, and heads might only come up 45% of the time, and then tails pops up 55% of the time. But theoretical means in the perfect world, when all things are equal, we should land I guess whatever outcome we're talking about evenly to the total possible outcomes. Okay, so here a fair die is rolled and the value of the uppermost side is recorded. Calculate the theoretical probability that a 4 is the uppermost. So how we write this is P event, or PR in some textbooks. So the probability of a 4 is 1 on 6 because there's only 1 4 on a dice. And then there's 6 numbers on a dice. Okay, so total possible outcomes is 6. Well, if we want a 4, there's only 1 4 on a dice, so that's why it's 1. Complementary events. So 2 events that are complementary to one another means they add up to 1. Okay, so if we have a little dash above the capital A, that means not A. If we have A, that means the probability of A. Let's put it to an example and see what happens. So a player is chosen from a cricket team. The events selecting a batsman and selecting a bowler. Complementary events if a player can have more than one role. Does that make sense? Did I misread that? A player is chosen from a cricket team. The events selecting a batsman and selecting a bowler. Complementary events if a player can have more than one role. Right. So remember, complementary events are like heads and tails. All right. The probability of a heads is 0.5. The probability of a tails is 0.5. Together, they add up to 1. But here, when we're selecting a batsman and a bowler, it is not a complementary event. So, not complementary. Okay. Why? you could be the wicket keeper. So wicket keeper. Can be chosen. Number 2, okay, you could be both. You can be both a batter or a batsman and bowler, which means there's no way we can have them complementary. For example, that's like saying, well, we can flip a coin and you can both get a heads and a tail at the same time from that one coin. Not possible because they are complementary of one another, meaning you get either a heads or a tails. Here, when we have a batsman and a bowler, well, you could be a wicket keeper. You could be both batsman and a bowler, or you could be neither, and you could just be like a coach or some other role. All right, so that's why these two events are not complementary. It's probably not a great example to use the sporting context, especially if you're not familiar with cricket. Okay, but just remember, complementary means the outcome of 2 or more things add up to 1. Okay, so what else? Probability of getting probability of getting a 1 on a dice and probability of not getting a 1 on a dice. That would be complementary because they add up to 1. That's all for 11.2 for now. It's quite a long exercise, so just do all the questions that have worked example 4, attach them, and then we'll carry on Wednesday. Thanks, everybody.